Hi everyone, this video is on vectors and more specifically on linear dependence and independence. So I'm just reading from the summary that you have access to. It says vectors are linearly dependent if at least one of its members can be expressed as a linear combination of other vectors in the set. So when you've got two vectors, we know they're linearly dependent if they're parallel. But when there's three vectors, we have to prove that the formula that's given here, C equals MA plus NB, where A, B and C are all vectors, yields a result. So then we need to find a value of M and N that are scalars that make this true. So I'm going to just scroll down to this, and I'll do this example here and hope that I get the same answer that's in the summary. So we're told that vector A is 2, -5. We're being told that B is 3, 7, and C is 2, 5. And we want to show that there exists two scalars, M and N, such that that formula is true. So we want M times 2, -5 plus N times 3, 7 to give us C. And C is 2, 5. And we want to show that there exists two scalars that make this true, M and N. So that's setting that up, that equation. So if we expand this out and put that in linear equations rather than with these matrices, we'd simply get 2M plus 3N equals 2. So that's just looking across the top row. And the bottom row gives us -5M plus 7N equals 5. That's that bottom row. And we just have to see if there's a solution to this. And generally speaking, it's not enough just to find that there is a solution, but to actually solve for what M and N would be. If we were just showing that there was a solution, we could simply think in a matrices sense and find the determinant and show that it's not 0, or we could just go through and find M and N, which is what we're going to do now. So I can solve these simultaneously. So I'm going to multiply the top equation by 5. So I get 10M plus 15N equals 10. And I'm going to multiply the bottom equation by 2. So I get -10M plus 14N equals 10. So what we're doing here is ensuring that the M coefficients have the same magnitude, not necessarily the same sign, but that's so I can eliminate them. So if I then add those two equations, the M's go away, I get 29, N equals 20, N equals 20 on 29. Let's see if that's correct. It is indeed. I then sub that back into one of the equations. I'll use the top one. So 2M plus 3 times 20 over 29 equals 2. 2M equals 60, plus 60 over 29 equals 2. 2M equals 58 over 29, take 60 over 29. 2M equals -2 over 29, so M must be -1 over 29. And that's what I got there. So the fact that we've found a value of M and a value of N means that they have to be linearly dependent. Because if there is a solution, then it is linearly dependent. So now moving to linear independence, which is just the opposite of what we did up here. It's the opposite of linear dependence. So with linear dependence, we want to find that there is an M and an N that make this true. And in linear independence, we simply want to show that there is no M and N that make it true. So I'm going to use a 3-component vector situation for this one. And I'm just going to talk you through the solution that's in the summary. It should hopefully make sense. So in this case, we set up the equation again. So M times A plus N times B equals C. And we get, just like we did here, where we took out each row and made it into an equation, we get 3M plus 2N equals -1. That's the top row. 4M plus N equals 0. That's the middle row. And then -1M, so -M, plus 3N equals 1 for the third row. Now we've got 3 equations, but only 2 variables. So we only have to use two of the equations to find m and n, and then just test it for the third one to see if it's true. So if we solve the top two equations, we get m equals a fifth and n equals negative 4/5. Now I'm not going to do that here because I showed you an example of doing that up here. It's just simple elimination using two different equations. So we get the m and the n. However, if we put the values of m and n into this third equation, we'll show that it doesn't fit. In other words, if we put m equals a fifth, so negative m, plus 3 times negative 4/5, that's negative a fifth plus 12/5, that's negative 13/5, not 1. We needed it to equal 1. So that shows that we do not have a value of m and n that makes this true. So therefore, they are linearly independent, not linearly dependent, like the example I showed up here. So dependence and independence linearly is just using this equation and either finding an m and n that makes it all true, which means it's linearly dependent, or not finding an m and an n that makes it all true, in which case it would make them linearly independent. Hopefully that makes sense.